Ni hao. Hello. This is the first part of the 21st lesson in heat transfer. In lesson 21, we will be discussing internal flow convection heat transfer when the tube wall in which the fluid is flowing is subjected to a constant heat flux. This boundary condition is a common one found in many applications. This boundary condition is also found in the example that we discussed in lesson 20. That example is a solar parabolic trough concentrating collector. In a solar parabolic trough collector, a fluid flows through an absorber tube. The absorber tube is subjected to an approximately uniform flux due to the concentrated sunlight from the parabolic mirror. By the end of this lesson, you should be able to sketch the surface, center line, and mean temperature of fluid flowing in a pipe subjected to a constant flux on its wall in the direction of flow. You should also be able to explain how engineers identify fully developed thermal conditions in this particular case. On with the lesson.
I want to turn to the handout. So we're going to kind of put we still need the T sub R thing on hold for a little bit. And I want to turn and think about this parabolic trough concentrator unit, which I introduced on Monday. So I've got a picture here of Nevada Solar 1, and I grabbed some data from Nevada Solar 1 in terms of what the concentration of the parabolic trough concentrators in that plant are. It's 20 suns. We have 20 suns, which means that the flux applied on the absorber tube is 20 kilowatt per square meter. And I looked up information about the viscosity, the conductivity, the specific heat, et cetera, of the heat transfer fluid, and the flow rate associated with those concentrators. Oh, and the diameter of the absorber tube. It's 70 millimeter diameter tube. So they're pretty big, right? 7 centimeters, but they're big concentrators. Okay. And on page 2, what I want you to do is it's a very good approximation to say that the concentrator applies essentially a constant heat flux on the surface of the absorber tube. Right, so we're concentrating light down onto that black absorber tube on the inside of the glass envelope, and we can think about the flux being constant along the length. Right, so the radiation is being absorbed on the absorber tube, and we can think of it like this constant flux all along the length of 20 kilowatt per square meter. Right, and so we have fluid that goes in one end of the tube, and we're going to say it goes in hot, right? And it's flowing down the tube, and of course it's being heated up as it flows down the tube by the concentrated light on that's being absorbed at the absorber, and it comes out hotter, right? It comes out warmer on the other side. So you don't necessarily know the answer, but I want you to think about this. But I do want you to make an educated guess and perhaps take some inspiration from this picture here, okay? And what you know to be true about open thermodynamic systems, and the fact that we know that this energy is going in, right, across the walls. And make a sketch for yourself. How do you think that the temperature at the inner surface of the tube, so here at R equal big R, right, at the inner surface of this tube, how does that change as the fluid flows down this tube and is warming up? And also, how do you think that the temperature changes at the center line here, right, where R equals 0? So as the fluid is flowing down this tube, how do you think the temperature at the center line is changing as we flow down? Like, what's happening there? And then I want you to think, how does this mass average temperature or the mean temperature of the fluid change as we flow down the tube? So of course, there is no radial dependence on the mean temperature, right? Because it represents some average temperature at any particular section of the tube. But if we had to plot that as a function of x, which we can do, how does that change as we flow down the tube? knowing that we have essentially a constant flux condition at the surface. Asking those questions are kind of important, right, for the design of a parabolic trough concentrating unit. Like we have to know how these temperatures change. So just think for yourself, make an educated guess. I'll give you some time to do that, and you can talk to each other too. Alex.
What's the developer inlet?
You asked about the developing length?
Is it developer inlet?
Yeah, that's incorporate that into your thinking. No. We're going to say it comes in at a uniform velocity and a uniform temperature. Okay.
Now, what I would like you to do is pause the video and write down an answer to the question.
I'm just going to sketch. I won't ask you to tell me, but I'll sketch some of the things that I saw. Right. So I saw in a lot of sketches thinking that the center line temperature would look something like this. Right. So there's this initial region in which there is no change in the center line temperature, and since it's coming in at all mixed up at 400 C. Everything's got to start at 400 C, right? So it starts at 400 C. And some of you told me that you think it starts this way because, right, the energy is coming from the outside in. And so it's going to take time for the thermal energy to reach the center line and raise the temperature there. So in essence, you're thinking there is a thermal boundary layer that will develop. Yeah. So, and wherever that center line temperature starts to increase, that's got to be where the thermal boundary layer has collapsed in the middle, right? So like if we're thinking about, you could even sketch the little thermal boundary layers, and we know that right at that location, wherever you have it, that's where the thermal boundary layer meets itself, where the center line starts to increase, right? Because the energy's made its way all the way into the center at that point. I saw more variation in the other two lines. So I saw some surface temperatures that were the same, that were constant. I saw different things about the mean temperature. Some I saw for the guesses, the mean temperature looked like this. Okay, so we had mean temperature. These are all just guesses, by the way. So we're going to work out what this has to be in reality. But don't sketch what I'm sketching if you want to save it for like what actually happens in the end. So I saw mean temperature guesses like this. I saw mean temperature guesses that were just straight lines up, right? And then I saw surface temperatures were kind of all over the map, which is good. So I saw straight line surface temperatures like this. I saw surface temperatures that were increasing. So I just asked you to make a guess, right? So you don't necessarily know the answer anymore. But my real point in having you do this, one thing that none of you I think drew were, with the exception maybe of a few, most of your curves increased in the flow direction. Yeah. So the temperature, if we think about the partial derivative of the temperature with respect to x, it was not equal to 0. Yeah. Like the temperature is increasing in the flow direction. So now I want to ask you the question, if that's the case, you all seem to have gotten there and agree that that's the case. We defined fully developed conditions hydrodynamically as the place where there's no more acceleration or deceleration. There's no more change in the velocity. Yeah. So do we ever even have fully developed thermal conditions if you agree that the dt dx is not equal to 0? Is it even possible for us to say there is such a thing as fully thermal developed conditions? Alex?
We have steadily developing thermal conditions.
Okay, so it continues to develop, but somehow something is steadies out. So there is some transient thing that decays. Okay, Daniel?
This goes towards basically this, if you just adjust what you consume, you just slide it up and down as far as temperature, and they look the same.
I think,
it's like increases, but the profile is like the same.
yeah, so Daniel had a nice thought. So let me try to repeat back his thought to you. He said the temperatures may be increasing, but the profile, right, the shape of the temperature curve doesn't change anymore. So it may, even though that the temperatures may be increasing, I think of shapes as kind of like differences between two locations in temperature. So what his guess was, or what he thought about was, he said, okay, look, eventually, I think that we're going to get to a place where all the temperatures are increasing, but they're increasing at the same rate. And so the relative difference between temperatures at any location stop changing. So the difference between the centerline temperature and the mean temperature, or the difference between the centerline temperature and the surface temperature, eventually these become fixed differences. So even though dTdx is not equal to 0, there is something, like Alex said, something stops changing in time. Something becomes steady, so to speak. And if you want to think of it this way, you could say like there becomes a steady increase in the temperature, right, in the flow direction. Right. So this is going to be what we call fully developed, and that's going to happen way over here. As soon as the thermal boundary layer reaches itself, we're going to see this condition. Okay. So now I'm going to try to convince you that that's the case. But first, let's just I will at least, yeah, I'll try to convince you of that. But first, let's unpack what this like constant difference means. So first, this next question on there is it ever possible? And yes, for the reasons that I just described. Okay, so while the fluid temperature at any radial location within the tube continues to rise, right? So there is a non-zero dTdx. The relative difference between the temperature at any two locations becomes independent of the position. Or another way to say that is, like Daniel said, it is the slope of the T profile is constant in the flow direction. So let's talk about how we characterize that. So if we wanted to write this mathematically, what you'll see is we're going to write, instead of d, like we had du dx equals 0 for the hydrodynamic case, for the thermal case, and this is where you probably want to write this down in your notes. We'll have the partial derivative of a kind of a dimensionless temperature. Of those three temperatures that we were thinking about, and we're going to say that becomes 0 for fully developed conditions. And you can think about this thing in the parentheses as a dimensionless temperature, because that's what it is. So let's unpack this a little bit, and to do it, we're going to have to do some chain rule work on this derivative. And to make that a little easier, I'm going to rewrite this into a little bit different form to make it easier to see the pieces. So what I have is the derivative of Ts minus T times Ts minus Tm to the -1, right? Has got to equal 0. So let's apply the chain rule. So I'm going to take the derivative of the first term, right? And take the derivative of the first term, but the second term doesn't go away. So I have the derivative of the first term would be the derivative of the surface temperature. Ts, by the way, is surface temperature. Tm is the mean temperature. T is the temperature at any other spot. So if you want to write that down, so Ts is the surface temperature. Tm is the mean temperature, the mass average temperature. And T is the temperature at any other radial location. Could be the center line, could be halfway between the center line and the wall, any other spot. Okay, so we anticipate that, you know, the surface temperature is going to be changing as a function of x. And then I have a dt dx left over, right? All of that's going to be divided by the thing that was left over, the thing that we say is a constant. So it's over Ts minus Tm. And now I've got to take the derivative of the other term, right, from the chain rule. So I'll have this thing left over, Ts minus T, times the derivative of this thing. And now I have to do another, like a chain rule and a chain rule, because I really have the derivative of 1 over something. So I've got to take the derivative of the total thing. So it's like the derivative of x to the minus 1. So I'm going to end up with, that's where the minus comes from, this thing over Ts minus Tm squared times the derivative of the stuff on the inside. So dTs dx minus dTm dx. All of that's got to be equal to 0. And because I have a Ts minus Tm in both of these, I can get rid of one of them. So I can get rid of that one and change this into a 1, right? Multiplying both sides of the equation by Ts over Tm. And now I'm going to solve this for dt dx. Okay. That's going to give me another equation. So when you take that and solve for dt dx, you end up with this Ts minus T over Ts minus Tm, our dimensionless temperature, times the derivative of the mean temperature in the flow direction minus Ts minus T over Ts minus Tm, our dimensionless temperature, times the derivative of the surface temperature in the flow direction plus dTs dx. So all we've done is applied the chain rule to our fully developed statement of what it means to be fully developed thermally, and broken it down into these individual terms. So now there are kind of two boundary conditions of interest. We're thinking about the constant flux one, which we'll talk about, but there's also a constant temperature one. So we're going to look at that. So you can write this down. There are two boundary conditions of interest to us. And we want to find out how dt dx and the mean temperature, all right, gradient are related in both cases. So our two boundary conditions of interest is, one, we say the surface temperature of the tube is constant. That's not the case for our parabolic trough concentrator, but that is going to be the case in other problems. And the other is our constant flux case, okay? That is our parabolic trough concentrator. So let's look at case A. So in case A, from equation 2, so like if you look at our equation 2, if we say that the surface temperature is a constant, what's true about the derivatives of the surface temperature in the flow direction? So if Ts is equal to a constant, then dTs dx is?
Zero.
It's got to be 0. Thanks, Nathan. So those terms just drop out. So in case A, right, our condition that relates kind of this partial of T with respect to X, the slope of the temperature at any radial location in the tube, it's got to be equal to Ts, this dimensionless temperature, over Ts minus Tm times dTm dx. Right. So this is in your textbook, it's equation 833. Right? And this is true when the surface temperature is equal to a constant. Right? Case B is a little bit more complicated, but we'll get there, and we'll get a really nice result that'll hopefully convince you that what I've drawn here has got to be the case. Okay, for our guess. Basically, we're going to check our guesses here. Right. So in case B, we're saying that we're in the fully developed region, and in the fully developed region, the convection heat transfer coefficient and the flux are constants. I'll try to convince you of that, I guess, in thinking about it. So if we have this thought, if we write this Newton's law of cooling down, and we have this idea that somehow Ts and Tm must both increase at the same rate, then it makes sense, right? If this is a constant and this difference is a constant, H must also be a constant, okay? So if I take the derivative of this equation with respect to x, Ts minus Tm, like this is going to tell me this is all equal to a constant, right? And so that what that tells me is that it's like dTs dx minus dTm dx has got to equal 0, right? Because the left-hand side is a 0, h is a constant, can't be 0. That means that this difference must be 0 in the derivative case, because it's got to be, the whole thing's got to be equal to 0. So that means that dTs dx has got to equal dTm dx in the case B. So just from that kind of logic that we anticipate that this difference has got to be fixed, those slopes have to be the same. So now we're going to take this idea, right, and put that into equation 2. Right, so if dTs dx and dTm dx are equal, what happens to the first two terms? Chase? They cancel each other out. And so what we're left over with is that this partial of t with respect to x has just got to equal however the surface temperature changes, right? And so I'll go up here. Don't have quite some space. So when that's the case, what we end up showing is that dTx is equal to dTs dx, but we just convinced ourselves that that's equal to dTm dx. So what does that mean for us? It means that in the fully developed region, the slopes of all the lines are equal, right? The slope of the temperature and the flow direction at any radial location has got to have the same slope of the temperature at the tube wall surface, and it's got to have the same slope as the temperature of the mean temperature. So now we can kind of, if you want, you can go back, right? And we can fix our guesses quick. So let's draw this in, right? With one other idea, and I talked to some of you about this. From the first law, this is the last thing for today, okay? From the first law, right? If we remember that the mean temperature represents the enthalpy flow rate of the fluid, if we have a constant flux condition, right? It's like we're adding the same amount of energy, right? Every step of the way down the tube. And so we're increasing the enthalpy of the fluid, right? Linearly, right? It's a constant increase as we go down the tube. So we can pretty much just from the first law argue that the mean temperature from the get-go, the mean temperature has to be increasing linearly as we flow down the tube. Yeah, I didn't do a very good job of making it long enough to get over to the other side, right? But the mean temperature has to increase linearly, right? Must increase linearly from first law arguments. But now we've convinced ourselves that in the fully developed region, right, dTs dx has to be the same. So the surface temperature has to have the same slope as whatever we've drawn for the mean temperature line. And the dTx, this, which is the slope at any other radial location, also has to be the same. So the center line is another radial location, right? So the center line temperature has to also be increasing linearly like that. So then the question is, what happens? Sorry, gotta get it here. Center line temperature. What happens up to that place on the center line? Nothing, right? Because the thermal boundary layer hasn't met itself. But as soon as it becomes fully developed, bam, center line temperature starts to increase at the same rate. Now, what happens to the surface temperature in the entry region? Right, we're going to talk about this more on Friday. But in the developing region, H is not a constant, and in fact, H is going to be larger in the developing region than in the fully developed region. And so in the developing region, the difference between the mean temperature and the surface temperature is actually going to be smaller than it is when it becomes fully developed. And once it becomes fully developed, that difference is going to be fixed. Okay. Chase.
Wait, so is that like, is that like curving up like that? In,
Yes.
In the development?
Yes. Yep. It's a curve up. It's a curve up from the entry point to the fully developed location. So over here, we're developing. And then here we have become fully developed. And we just made the statement that basically differences in temperature are not going to change. Now, this all goes out the window when we change the boundary condition to become isothermal. Okay, that's going to be more complicated. We'll have to talk about that more.